In Chapter 12, we are now going to be looking at when we want to find out information about a population mean. So chapters 12 and 13 kind of mirror the same thing that we learned in 10 and 11, where we were actually looking at categorical data in the previous chapters. Now we're going to look at numerical data and how do we find confidence intervals or hypothesis tests using that. Okay. So when we are looking at a sampling distribution of a sample mean, we want to make sure again that we understand all the vocabulary and all the symbols that we use. So we know n is the sample size. Remember that x bar is the mean of a sample. S is our standard deviation of the sample, and then mu and sigma are the mean and the standard deviation of the entire population. So when the purpose of a statistical study is to learn about a population mean mu, we estimate mu with x bar. And so if we understand statistical inference procedures based on x bar, then in order to do that, we have to look at how the sampling variability causes x bar to vary from one sample to another. Okay. And we do this for confidence intervals or hypothesis tests. The sample size n and characteristics of the population, right? Its shape, the mean, the standard deviation, those are all important in determining the sampling distribution of x bar. So remember, we have looked at a sampling distribution of a proportion before. Now we're going to look at the standard deviation, or the sampling distribution of x bar. Okay. So let's look at this example. There was a paper written called Mean Platelet Volumes in Patients with Metabolic Syndrome and its Relationship with Coronary Artery Disease. And it includes data that suggests that the distribution of the platelet volume for patients who do not have metabolic syndrome is approximately normal, with the mean mu is equal to 8.25 and the standard deviation is 0.75. So here's a graphical picture of it. Mu, our center value, is 8.25 and our standard deviation is 0.75. So what values for the sample mean would we expect if you were to take a random sample of size 5 from this population? So just like we did this with the population, we're going to do it with the, let me get off this page and then come back because it's messed up. There we go. We're going to do it with the sample mean. So a statistical software package took 500 random samples of size n, or n equals 5. And this was the distribution that we got. So we have a density histogram. And remember that the mean was 8.25 of the population. And so if we look, here's 8.2. So we have our mean tends to be around the actual population mean. But we got some means that were down here and some means that are way up here, by 9.1, and one was 7.3. So the sample means weren't always close to the actual population mean, but most of them were. Right? So again, we know that a sample of size 5 doesn't really give us a really good picture. But if we increase the sample sizes, here's our size 5, n equals 5. Here's n equals 10. n equals 20. These all look very normal, right? We get to n equals 30. But what's happening with these distributions? Okay. The means of the distribution all seem to be about the same, right? But what about the standard deviation, the spread? As you pick a higher value for n, what happens? As n gets bigger, the standard deviation gets smaller. And what do you know about the shape? Well, the shape looks approximately normal. And that's always a good thing because we want to be able to use what we know about the normal probability distribution to make decisions. So how about this example? The paper, is the overtime period in an NHL game long enough? Okay, so this paper gave data on the time in minutes from the start of a game to the first goal scored. This was for 281 regular season games from the 2005-2006 season that went into overtime. So this is the density histogram. So what we're going to do is consider these 281 values as a population. The distribution is strongly positively skewed, right? When we look at this data, very positively skewed. The mean is 13 minutes and the median is 10 minutes. So now, again, using a statistical software package, 500 samples of size 5, 10, 20, and 30 were selected, and a histogram was constructed for the mean value for each of the 4 sample sizes. Okay, so when we look at this, even though the data was skewed, right, positively, when we look at n equals 5, n equals 10, it still kind of looks skewed. As we get to n equals 20, it looks a little bit skewed, but it's getting to look normal, right? So really all of the distributions seem to be centered at mu equals 13. Even though it doesn't look as normal in n equals 5 and n equals 10, we still have the values centered about 13. So these also look approximately normal, especially as we increase sample size. And as the sample size increases, we see that the standard deviation decreases. So even though we had skewed data, our sampling distributions seem pretty normal. And the mean of the sampling distribution seems to be the mean of the population. And our standard deviation of the sampling distribution seems to be the standard deviation of the population divided by the square root of n. And we're not going to really get involved in how that is calculated. We're just going to use it as our rule. And this rule is exact if the population is infinite and is approximately correct if the population is finite and no more than 10% of the population is included in the sample. So we have the same conditions as we did before when we talked about the proportions. And I don't want you to worry too much about those because for this introductory course, we're going to follow these guidelines. And then finally, our rule number 3. When the population distribution is normal, the sampling distribution of X bar distribution is also normal for any sample size n. So we can see in this picture, this represents the population mean and standard deviation. This represents when n equals 4 and when n equals 16. And so we have what we call this final rule, the central limit theorem. So the central limit theorem says that in this case up here we had the population was distributed normally. But down here, the population is not distributed normally, it's skewed, right? But as n gets larger, our sample actually becomes normal. So the central limit theorem, which is really, really, really important in statistics, says that when n is sufficiently large, the sampling distribution of X bar is well approximated by a normal curve. Even when the population distribution itself is not normal, which is pretty nice because a lot of times we know that the population that we have isn't normally distributed, but we can still use the information about the normal table and the z-scores as long as we can have a large enough sample. Now, how large is the sample we need to have? A good rule of thumb that statisticians use is that as long as n is greater than or equal to 30, then the central limit theorem can safely be applied. So let's consider these rules in this example. In a study of the courtship of mating scorpion flies, one variable of interest was courtship time. Okay, so we're talking about time. This is a numerical variable, right? So this was defined as the time from the beginning of a female-male interaction until mating. Data suggests that it's reasonable to think that the population mean and standard deviation of X bar are mu equals 117.1 minutes and sigma equals 109.1. So if the population mean and the standard deviation of remember that Rule 3 says that when the population is normal, then the sampling distribution is also normal for any sample size. So do we think that it is approximately normal? So, since this is pretty large, right? I would think that, if the mean is 117 minutes, but the standard deviation was 109 minutes, right? Compared to a mean of 117 minutes. So if the standard deviation is very large, then I think that there's probably outliers, which could mean that we don't have a normal distribution. So I would say there may be outliers which could mean the data is not normal. So remember that Rule 4 says we can use the central limit theorem when n is greater than or equal to 30. Okay. So what was our sample size? Our sample size was 20. So I would say that it is not reasonable to assume the shape of the sampling distribution of x bar is normal. Okay, so when we have a small sample size, or whenever we're testing about a mean, we're going to have to be thinking about whether or not the data that we have is normal. If it's not normal, then we have to hope that we can use the central limit theorem. If we can't, we'll have to think about what we can do after that. But for right now, if we can have a sample size that is 30 or more, then we can apply the central limit theorem. So let's take a look at this example and see if we can do that. So we have a hot dog manufacturer, and this hot dog manufacturer claims that one of his brands of hot dogs has a mean fat content of 18 grams per hot dog. So we assume the consumers of this brand probably wouldn't be disturbed if the mean is less than 18 grams, but if it's more than 18 grams and they're saying that it's 18 grams, then people wouldn't be happy about that if they're trying to watch the grams of fat that they put into their diet. If they're really trying to watch the grams of fat they put into their diet, they're probably not going to eat a hot dog, but for the sake of the problem, we'll stick with it. Okay. So in this situation, what we're going to do is we're going to let x be our variable of the fat content of a hot dog, right? And we're going to assume that we know sigma is equal to 1 gram. So the standard deviation of the distribution is 1 gram. So an independent testing organization is asked to analyze a random sample of 36 hot dogs. Well, what does 36 hot dogs tell us? It tells us that the central limit theorem applies. So even if the population is not normal and maybe it's skewed, we have a big enough sample size that was greater than 30 so that we can approximate it with a normal distribution or sampling distribution. So the sample size of our distribution is 36. So it is large enough to say that the sampling distribution will be approximately normal. And the standard deviation of the sampling distribution is going to be sigma over the square root of n, and we said the standard deviation of the population up there is going to be 1 over, that's the square root of 36, so that'll be 1/6, which if we write that as a decimal, repeats for a while, and then we'll eventually round. So what we want to know is that if the manufacturer's claim is correct, then that means that mu is 18, which means that the mean of the sampling distribution is going to be 18. So this should be mu right here. Mu equals 18. So even we know that even mu equals 18, even though that's true, the mean of the sample that we get is probably not going to be exactly 18 because there's sampling variability. But is it likely that we would see a sample mean at least as large as, say, 18.4 when the population mean is really 18? Well, we can think about that by computing the probability in using the normal distribution and saying, well, what would happen if the probability that x bar was greater than 18.4? What would that probability be, knowing that knowing what we know about the mean and the standard deviation? So we could change this to a z-score and say, look for the probability, actually at least as large, so that would be greater than or equal to 18.4. So z would be greater than or equal to 18.4 minus 18, mu, over 0.1667, the standard deviation of the sampling distribution. So this is the probability that z is greater than or equal to 2.4. If we look that up on our z table, 2.4, I'm going to use my trick of that area. Remember that if z is 2.4 right here, this area is the same as saying negative 2.4 and looking at that area. So it's going to be 0.0082. Or if you wanted to, you'd look up 2.4. Because this is the area below that number, since we want the area above 2.4, we would take 1 minus 0.9918. We're still going to get 0.0084. Or I'm sorry, 80082. So 0.0082. So what this says is that values of x bar as large as 18.4 will be observed only about 0.82% of the time, right? So if we move the decimal over 2 decimal places, it's less than 1% of the time when we pick random samples of size 36. Okay. So what does that p-value tell you about the manufacturer's claim? Well, the value x bar equals 18.4. Now, if this was the sample that you got and you checked and it was 18.4, that p-value is, or the mean value is enough, is greater than, how do I say that? I guess enough greater than 18.0 that we should be skeptical of the manufacturer's claim. Okay, so what we've done is we've kind of looked at a kind of a hypothesis test where we were able to use the central limit theorem to create use the normal sampling distribution and the normal z-table to come up with a probability of whether or not this claim that this manufacturer has is really true. And so they probably did some fancy wrong statistics to make sure that they could say that the mean was 18. But probably it's likely that it's not, that I would be skeptical and that there's more fat in these hot dogs than what they're claiming.